So last time we talked about generators and relations for the symmetric group S3. Now more generally, what if we had the symmetric group Sn, where n can be any number, 2 or more. Now this is just a slight difference. So here's the theorem. So let n greater than or equal to 2. So I want to give generators and relations. So let n greater than or equal to 2, then Sn, the symmetric group, is isomorphic to the free group on n minus 1 generators. Okay, so let me give them a name now, A1, A2, An minus 1. So there are n minus 1 in all, and modulo the normal subgroup n generated by where n equals the normal subgroup generated by a short list of relations. So what are the relations we need? By the following elements. First, ai square. Okay, so this is like the a square and the b square that we had in the case of SL3. So this is ai square for I between 1 and n. Okay, so this is one set of elements I need. The second collection of elements I need are like the AB whole cubed that we had in the case of SL3. So that is the following. I take each generator AI and multiply it with sort of its adjacent generator, the next one, AI plus 1. So I look at AI plus 1 cubed. Now here I can go from, here it can go till n minus 1, here it can go until n minus 2. Okay, so this is the second sort of element I need in the kernel, and the third sort, which we didn't have in the case of S3 because it's too small, but here we will have it in general, is elements of the following form. So let's take any AI and multiply it by AJ and take the square of this element. Now what are I and j here? J can't be I plus 1. Okay, so j has to be greater than I, but sort of farther than just one step apart. Okay, so it's 2 steps or more from I. So here we say that I and j, well, let's say I and j are firstly between 1 and n minus 1, but j is at least I plus 2. So this is the third collection of elements you need, and well, between them together they give you a collection of relations. So they give you a set of elements, and the normal subgroup generated by this set is exactly going to be the kernel of the map from the free group to this. Okay, so let me sort of give you an indication of the proof, which is almost along the same lines as for S3. So the first thing is from the free group. So let F denote the free group on these n minus 1 generators. From the free group, we can define a map, a homomorphism to Sn as follows. It takes, so this is a homomorphism pi, like in the case of S3, A1 maps to 1, 2, A2 maps to 2, 3, and so on, till An minus 1 maps to the generator n minus 1n. Okay, and as before, this defines a homomorphism by the universal property of free groups. It's enough to specify it on these elements A1, A2, An minus 1. Okay, but the fact that you're mapping it to these transpositions implies in particular, so observe that just like in the case of S3, that each AI square is going to map under pi to the square of this transposition I plus 1. Okay, and a transposition of course has order 2. Okay, so each AI square maps to the identity. So AI square is in the kernel. If I take a pair of consecutive elements AI plus 1, where does it map? Well, it maps to the product of these two consecutive transpositions, but that's just a 3 cycle I plus 1, I plus 2, whose cube is identity. So therefore this cubed is just the cube of this product, which is again the identity. Okay. So thus far it's like the computation for S3, and now comes the new ingredient. If I take AI and AJ, two generators which are far apart, meaning not just one step apart but at least 2 steps apart, then their product maps to, well, what does it map to? It maps to I plus 1 times J plus 1, but these are now 2 disjoint transpositions. Okay, they have no elements in common because J is not I plus 1, it's greater than I plus 2, greater than or equal to I plus 2. So this is like a product of 2 disjoint transpositions, and this element still has order 2. So if we take the square of this, it's just going to give me the identity again. Okay. So that is where we got those relations. So AI square is surely in the kernel, AI plus 1 cubed is in the kernel, and AI AJ square is in the kernel. This is for J at least I plus 2. Okay, so we know for sure that the subgroup N that we wrote out, the normal subgroup generated by these elements, that is surely contained in the kernel. So what we know is that this normal subgroup N, like in the case of SL3, is contained in the kernel of pi. And again, one sort of proceeds in the same fashion as before. You know that F modulo the kernel is, well, there is an isomorphism to the group Sn, and since n is contained in the kernel, from F modulo n to this I have a surjection. Okay, just the usual, the same maps that we wrote out before. Gn maps to G kernel pi maps to pi of G. Okay, so you have these maps, and to prove that n equals kernel pi is the same as showing that this whole composite map is an isomorphism. So if we can take this composition here and show that this composite map is an isomorphism, then we are done. Okay, so that's what we still have to prove, and to prove that, so need to prove that this green arrow, so this green arrow is an isomorphism. That's the claim. Okay, and to prove that, I mean, the proof is still indirect like before, which is we show that F by n has at most the number of elements in Sn. So claim, the proof proceeds via a counting argument. We show that this can have at most n factorial elements, and recall that's the cardinality of Sn. Once you show this, because there is a surjection, it has to have at least n factorial elements. And the claim now, so the claim, further claim is to say it has at most n factorial elements. So together it will show that it has exactly n factorial elements, and then you proceed like in the case of S3. Okay, so now I'm sort of just going to indicate how to do this. You have to proceed as in the case of S3. So the proof proceed as in the S3 case, as in the case of S3. Okay, which is that you have to write out all the different possible cosets of elements of this kind. Look at Wn and write out what are all the possible cosets. So look at all this. W is a word, any element of the free group, and now you will have to count the cosets and show that there can be at most n factorial of them. So I would sort of say the hint is first do it for S4, and that will sort of tell you how to do the general case. And for S4, let me just tell you what is it that you have to prove. So here I have 3 generators in the case of S4. So recall I had A1, A2, A3, these are the 3 generators. So maybe it's easier to, let's just rename them as A, B and C in the case of S4. So what we had in the case of S3 was the following. We said look at the following 6 cosets. So those very same cosets will also be required here: A, N, B, N, Cn, sorry, there is no C here, An, Bn, Abn, Ban, and Aban. So these 6 cosets were what you need in the case of S3. Now in the case of S4, we will need 24 cosets. Okay, what are the 24? Well, these 6 certainly are there. In addition, we also need this look at what I call CT, which is the very same 6 cosets with C multiplied on the left. Dot dot dot. Same thing with, so look at BCN and ABCN. Okay, this will again give me a list of 6 BCN, sorry, BCT, I'm sorry. T was my set of 6 cosets. So BCN, then there was, so you have AN, look at BCAN, dot dot dot, 6 of them. ABCT again is, I take ABCN, so I had AN, so I just put ABCAN, dot dot dot. So I have 6 plus 6, 12 on this page and 12 on the earlier page. Show that these 24 cosets are all you need. Any other word that you write out in the A, B and C will always reduce to one of these 24. Okay, and the way to do it is sort of also an inductive process. Only look at words which have A's and B's to start with. Okay, and that's like the S3 calculation which we have already done. And now insert the C, and now put the extra C in and see what happens. Okay, so I'm going to leave this for you to explore and play with. So it's a very good exercise because it sort of gives you some facility in working with free groups and so on. Okay, but let me now move on to what's the application of this generators and relation procedure. So here are some applications. If you can realize a group by way of generators and relations, what it gives you is a way of constructing homomorphisms. That's the key use of having generators and relations. If I want to construct homomorphisms from my group Sn, okay, Sn is the group which I now understand in terms of generators and relations, I can construct homomorphisms from Sn to any other group G. Okay. How do I construct them? Well, here's the proposition. So I should say applications of the generators and relation procedure. It allows us to construct group homomorphisms from Sn to any other group. Okay. So what's the procedure? How do you construct a group homomorphism? Well, here's what you need to do. You need to find n-1 elements in your group G which sort of obey the same relations as the generators of Sn. Okay, so let G1, G2, Gn-1 be elements of G satisfying the following properties, that Gi square is the identity for all I between 1 and n-1. So this is the identity of the group G. Now Gi plus 1 whole cubed is the identity in the group G. This is for all I between 1 and n-2. And the third set of relations, which is Gij whole square, is the identity for all j at least I plus 2. Okay, and between 1 and n-1. So in other words, I find n-1 elements of my group G which satisfy the same relations in the group G that my generators of Sn are supposed to satisfy. If I can do this, then I am guaranteed there exists a group homomorphism from Sn to my group G such that which sends the corresponding elements of Sn. So what elements? The elements sigma I to Gi. Okay, where sigma i's are the transpositions, where sigma I is just I plus 1. Okay, so if you want to map the transpositions to any elements of the group G, those elements must satisfy the same relations that the transpositions do, and conversely that's all you need. If you have that, then automatically there exists a well defined group homomorphism. Okay, so let's prove this proof. Where do we get this from? Well, from the, we need to go to the free group to get this. Okay, we cannot just work with Sn itself to prove this fact. So observe that from my free group on n minus 1 generators, so I had the free group f of a1 a2 an minus 1. From that free group I always have a map to G. Okay, what map is this? Maybe we should call it something pi. This map just sends the generators ai to the elements, special elements gi, okay, for all I from 1 to n minus 1. So there exists a homomorphism, like this. Why does it exist? Well, from the universal property of free groups, I can always specify arbitrarily where I want to map my AIs, and that always defines a homomorphism. Okay, but recall that the GIs satisfy those special relations. So let n be the normal subgroup generated by those relations, normal subgroup generated by the set ai square, ai plus 1 cubed, ai aj square. So here I'm just suppressing the bounds, I mean the ranges for i's and j's, but I mean we've looked at this before. So normal subgroup generated by that set of relations. Then observe that since gi satisfy the same relations, it's clear that each of these generators, then ai square will map to gi square, but that's gi square is the identity. Okay, and so on. ai plus 1 cubed will map to gi plus 1 cubed, but then that was assumed to be the identity in the group. Okay, so in other words, all these relations are actually satisfied in G. In other words, each of them lies in the kernel of this homomorphism pi. Okay, by the hypothesis, by the given hypothesis on the elements Gi. Okay, now we are almost back to our usual situation. So what does this mean? So I have now a map from f by n to f by kernel pi, and f by kernel pi by the first isomorphism theorem, this is isomorphic to the image of pi. The image of pi is some subgroup of my original group G. Okay, so all this is just repeating the same arguments we did before. So I can get a sequence of homomorphisms like this. This is just Gn mapping to G kernel pi, mapping to pi of G. Okay, and pi G is a subset of G. So this is for all G in my free group F. Okay, so I get this sequence of homomorphisms. Now, what is it that we have? Well, we wanted to get a map from the symmetric group Sn to G. Okay, but observe that this f by n. So now comes our the use of our theorem. This last guy f by n, remember, is exactly isomorphic to the symmetric group, right? From f by n, recall, I actually have an isomorphism to Sn. Okay, and what does this isomorphism do now? We just have to unravel what this isomorphism does. So let me write out this isomorphism just on those special elements. So what was this isomorphism doing? Well, if I take the special generator AIN, it was mapping it to those the transposition sigma I. Right? This is how we defined that map. How did we prove the isomorphism between f by n and Sn? We defined a map from f to Sn which takes ai to sigma I. Okay, and so the coset AIN therefore was mapping to sigma IN just by the first isomorphism theorem. Okay, so now we are all set, because now we know what AIN goes to. It goes to AI kernel pi, which in turn goes to pi of AI, but pi AI by definition was GI. Okay, so we just have to stare hard at this equation. So of course this isomorphism is defined as going in this direction, but all I have to do is just think of the reverse isomorphism. I just take the map from Sn to this, which is the inverse of this map. So this map sigma I maps to AIN, maps to AI kernel pi, maps to GI. In other words, what I have done is to show that I have constructed a homomorphism from Sn to the group G, and this homomorphism takes the element sigma I exactly to the given element Gi. Okay, and that's what we set out to prove. That finishes the proof. So if you give me GIs with the correct properties, then I can construct for you a homomorphism from the group Sn to G, okay, which maps the sigma i's to the element, which maps these sigma i's to the elements Gi. Okay, so that's the crux of this proposition. So in particular, so here's one simple application of this. So here's a question: what are homomorphisms? So find all group homomorphisms from the symmetric group Sn to what I'll call C cross. So this is just the set of non-zero complex numbers under multiplication. Z is not 0, thought of as a group under multiplication. Okay, this forms a group because I have inverses and so on. So the question is, what are all the group homomorphisms that you can define from Sn to this group? Well, let's think of it as an application of our earlier principle. So what did we say? In order to define a group homomorphism from Sn to C cross, what I need to do is give you elements. So I know that I have these n-1 generators of Sn, and if I stipulate their images, so Z1, Z2, Zn-1, if I tell you where they map, then that sort of determines my homomorphism. So we need find all group homomorphisms is the same as saying find, so I am rewording the question, find all collections of Zi 1 to n-1 of complex numbers, non-zero complex numbers, satisfying the following relations, that all Zi squares are 1. So 1 is the identity for the multiplication operation, and Zi plus 1 cubed is 1, and Zj square is 1 for all j greater than or equal to I plus 2. Okay. So these two problems are actually equivalent. It's enough to do this. So this thing that I wrote here is the same as the original question. Okay, that's the beauty of this. So just homomorphisms are just these n-1 tuples of special elements which satisfy the correct relations. Okay, now it's easy. We just have to find such complex numbers. So observe, Zi square equals 1 for all I means, of course, that what are the conditions? We conclude Zi can only be plus or minus 1 for all I. Okay. Now if Zi is say minus 1 for all I, so here are two cases, either Zi equals 1 plus 1 for all I. Okay, that gives me one obvious homomorphism, which is that the identity homomorphism, everything maps to the identity. So this is a valid choice because sigma I maps to 1 for all I means the homomorphism from Sn to C star is just every permutation maps to 1. Okay, because I can write any permutation as a product of these simple transpositions, and if every transposition maps to 1, then every element has to map to 1. So that's case 1. Case 2, suppose Zi is minus 1 for some I, just a single I. Then I need to figure out what are my choices. Is this a valid choice of Zi? Well, at the moment I only used one relation. I still have other relations, which is Zi plus 1 cubed is 1, Zj square is 1, and so on. So let's try and use the cube relation. So let's look at Zi plus 1. So if I is not n minus 1, then I will have something next to it, the next guy. So observe Za plus 1 cubed is supposed to be 1. Well, what does this mean? If Zi is a minus 1 and the product cubed is 1, then the only way out, and Zi plus 1 is also plus or minus 1, right? So there is only one choice. Both Zi and Zi plus 1 must have the same sign. If they have opposite signs, their product is a minus 1. So this means that Zi and Zi plus 1 have the same sign. In other words, since Zi is minus 1, this means that Zi plus 1 also has to be minus 1. Okay. Likewise, so I can replace I by I minus 1 and conclude that Zi minus 1 is also a minus 1. Okay, because it's the adjacent guy, it's the previous guy. I can apply the same relation with I minus 1 in place of I. Okay, and we keep going. Since Zi minus 1 is minus 1, the one before it, which is adjacent to it, must also be the same sign. Since Zi plus 1 is minus 1, the one after it must also be the same sign, and so on. So on the one hand, you keep going forward, and on the other hand, you sort of keep going backward. And this argument says, as soon as one of the Zi's is minus 1, everybody after it is minus 1, and everybody before it is minus 1. Okay, so this finally implies that every single Zi is, so Zj has to be minus 1 for all j. Okay, so this is the only other possible homomorphism, and again, what does this homomorphism look like at the level of what does it do to the other elements of the symmetric group? So if I take Sn to C hash, so I've said sigma 1, sigma 2, sigma n minus 1, all the simple transpositions map to minus 1. That's what this homomorphism does. But what about the other elements? What if I take an arbitrary permutation in Sn? What does it map to? Well, what am I supposed to do? I take that arbitrary element and I write it as a product of the simple transpositions. Okay, and this map phi is, well, what is it? Phi g is plus 1. Well, it's always plus or minus 1, but it's plus 1 if g is a product of an even number of transpositions. Of an even number of simple transpositions. Okay, these simple transpositions are just the sigma i's, and it's minus 1 if, well, if this is an odd number of simple transpositions. Okay, and recall, this is exactly the thing that you have seen before. This is the sign map. This is the sign of a permutation, which is if you write it as a product of transpositions, whether you have an even or an odd number of them. Okay. So what we have proved, therefore, is that there are just two possible homomorphisms. So the question was, find all homomorphisms from Sn to C star. Turns out there are exactly two of them, okay, which is the identity, which takes everybody to 1, and the other which takes everything to a minus 1.